super thin moon. Tell a little bit about how small of a crescent you can actually see or find. Talk a little bit about what makes it a real challenge, and this is a challenge that I have taken on, and I do it. And it's a challenge that has lasted me for many, many years. And then I talk a little bit about how I find a super thin moon. And I think sometimes beginner sections are good that way. If somebody has done something, say, hey, this is how I did it. And it's not the perfect way, it is a way to do it. And then at the end, I'll show a few of the images that I currently have. The thing that really triggered this talk is I got the arrival of this wonderful book in the mail. As a member of the RASC, one of the benefits is you get this booklet, and in it you'll find the Messier list, which you do your Messier certificate for. It's got the list of options for the NGCs and such. It doesn't have any super moon list or anything of that sort, but it has all the information you need in order to create, or in order to find out the information you need for a super moon. So the first thing I did is I kind of listed all the time frames of the new moons for this upcoming year, or for this year. There they are. You notice that the time of the moon varies quite a bit, and that plays into the fact that sometimes you can and sometimes you can't see a supermoon. Okay, so here's the questionnaire. I told somebody there's a questionnaire, and here's the quiz. So, what is the thinnest crescent moon you ever saw? What is the thinnest moon? It could be in the morning or it could be in the evening that you've ever seen. So, who's seen one like this? Pretty well everybody. How old do you think this is? Anybody?
2 days.
This is actually 30 hours. This is pretty good. You notice one thing about it? The nice earth shine up there. So actually, if you exposed it just for the part that the bright part that has the light on it, it would be fairly thin crescent. That's not what I'm after. How about this one? 24 hours. And the point is, right about the 24-hour mark, that's when the moon is old enough that you can just barely start to see the earth shine on it. That's not what I'm after. Notice all the clouds there, and then right at the bottom here, right here, you can actually see that there's a horizon, and that's clouds in the distance. So that's, if you think that's half a degree, that's sitting just a couple degrees off the horizon. That's not what I'm looking for. That's not. Can you see it? Whoa. Okay, how old do you think this is? 20 hours. And this is actually, this is not my image, somebody else took that, but this is what I'm talking about, super thin moons. And I think a super thin moon is under 20 hours, and that's my goal. So as beginners, I'm not expecting you guys to all go after something this hard, but first thing you do is you got to practice your technique, get used to how to find these things, and then you'll do your search. So I sort of categorize it like this. What I showed you first was the thin crescent moon. They're lovely to see. I always enjoy the thin crescent moons. Then from the 20 to 24 hours, a very thin crescent moon. And that's the category I'm sort of stuck in right now, trying to get something better. Then you get the 16 to 20-hour-old moon, which is a super thin moon. And that's sort of where, that's my next goal. And that's what I'm talking about today. And then, under 16 hours, an ultra-thin crescent moon. So, this is a talk about how to go searching and how to find them. And because this is a beginner session, I think, starting with the thin crescent moon, similar to the first one, is a nice place to start. And January just happens to be an opportunity for that. The other thing I'm going to suggest is that there's 2 ways you can go searching. You can go searching naked eye, just try to find it there, or you can go searching with optical aids. Now I like to do imaging, and since with imaging you've got to get everything going and you've got a very short window, I usually do my searching with optical aids. And I will talk about searching with optical aids mostly. So there it is. So what are some characteristics of it? Well, okay, super thin moon, under 20 hours. So that's what I'm after. You can see the arch there. You can see how thin it is. That's the 180 degrees. less than 1% of the moon is being illuminated by the sun. So as you know, when you get the full moon, it reflects a lot of light. There's not a light being reflected by this thing. And then you'll notice that they're all sitting within an hour. So if you want to do a task with that, you go to, you set up, you look for it, and an hour later you're out of there, you can go continue your evening. This is a good one. Funny, the last thing is there's no perceivable features. With all that you read in the magazines and all the talks, and there's going to be 2 talks by Darren upcoming about the moon. When you look for this, you're not going to be looking for anything specific. All you're looking for is a thin crescent, because you really can't see any features in it. So this is sort of about the size of the moon that I'm talking about. I thought that this one is a 29-hour moon. This is sort of what I'm going to tempt you guys to take on as a challenge to go looking for. So what causes a super thin moon? Well, with the moon going around the Earth, there are 2 opportunities that you get to see this. And the super thin ones are the ones that I would suggest are 24 hours or less around the new moon. So you can obviously see it at 2 different periods, either before the new moon or after the new moon. So how thin can you see? And I heard a number of answers being thrown out about how thin they thought the moon is. And actually, here there are limits that somebody has calculated, and it's only when the moon is at least 7 degrees away from the sun. So you need at least that space. But that's not a lot. That's like 14 diameters of the moon away. That's a very small amount. And a recent studies basically calculated the same thing. They went and did their own research into it, and they find it's something less than 7.5 degrees away from the sun. And that there's reasons why you physically can't see it. And basically, with the sun shining on the rest of the moon and the craters all the way around the edge, they're actually blocking a lot of the opportunity for light too. The mountain ranges are actually blocking the light, so it prevents you from seeing the very thin crescent moons. So here are some of the records. Stephen O'Mara writes books, he writes articles for Sky and Telescope. The guy's got phenomenal eyes. Whereas you and I can see 6th magnitude, 6.5, he can see, I believe, almost 7.5. So he's got amazing eyes, and his best visually is 15 hours. Someone in Tehran went and spotted it with optical aid, 11 hours and 40 minutes with a large pair of binoculars there, Darren-sized binoculars, 40 by 150s. So in order to catch that, he's using fairly large optical instrument to get that. So this is a challenge. This is the thinnest moon ever imaged. Can you see that? Does it show up well enough? Yeah. It's not much of an arc, is it? This one is taken at exactly new moon. When this picture came out a few years ago, I thought, boy, is that ever cool. And then the way you do it is because at some point in time, the moon and the sun, the moon's going past the longitude of the sun, so at some point in time they're lined up. Generally, the moon is either above or below, so there's no eclipse. But if the moon lined up with the sun, there's a solar eclipse. But generally they don't align. So at that time, this guy determined he wanted to take some pictures. So good for him. So he made this setup, and the moon was just 4.4 degrees away. So he had this, obviously, to prevent any light from the sun getting through his optical system also while he's doing the searching. The other thing is, he took a picture of it, but he could never see it. It's so small, he could not, even if he knew exactly where it was, he could not physically see it. But I thought it's just kind of cool. And again, one of the points it points out is if you're going to be looking near the sun, and sometimes people look for Venus near the sun, it's extremely risky. So as a presenter, I have to pass along that risk. Be careful with the sun, it could damage your eyes. So there are 2 times every lunar cycle that you can spot a thin crescent moon. And how much of that crescent depends upon when the new moon is exactly. Now, since probably 15, 16 hours is a regular period of time, if the new moon is less than that amount before it's setting, you won't see it, and then you'll see it the following day, and it's like maybe 14 hours plus 24, so it's a 38-hour-old moon. So you don't always get to see these thin moons on either side, but there's 2 opportunities, and you have to find the ones that you can actually go after and chase. So in my case, trying to get a 20-hour-old moon is really a challenge because they don't happen very often. And there are better periods than others to search out. So you want to do it at the right time of the year. Plus we have, weather considerations. Spring is one of the times to go looking for it. And our springs are light, cloudy. And then our high latitude, being up 50 degrees, if we're closer, further down, they would be higher in the sky and easier to see. So there's challenges. And again, why is it so challenging? Because the closer we are to the new moon, the less the moon is reflecting, the fainter it is, the harder it is to see. Obviously, you're doing it right after sunset or just before sunrise, so the sky is very bright. So it's a very challenging thing to see. It's going to be low on the horizon, obviously, and then whenever you're looking through the atmosphere, when objects get very, very low, the atmosphere is so thick, it dims the object again. If there are any thin clouds, sometimes, if you have very thin cirrus overhead, you see the moon, fine. It doesn't really distract you at all. But if you're looking at it and they're out in the distance and they're at an angle, now you're looking through them and they actually look thicker than just very thin, transparent clouds. So any clouds are hard to see. And there are better times to be looking for certain ones because of some of the geometric of it. So there are times, this one is saying it's easiest to see the youngest crescent moons in the springtime and in the fall. In the springtime, it occurs in the evening, and that's my prime time, evening observing. In the fall time, it's best to see it in dawn, in the morning. That's when it's higher, and this is why. Yeah, so I don't do very well with, anybody who's done observing with me knows I'm not a morning person, so I don't get up at 6 o'clock in the morning to do these things. So it's called the ecliptic, and that's the angle that the sun is traveling the path through the sky. So you can see here that in the springtime or in the fall time in the morning sky, the ecliptic is like this, it's very high. So any object on the moon being close to the ecliptic will be higher, much higher than it is here. The other thing I wanted to mention about this is that since we do know that the moon travels up and below, and I'll show you how much, up and below the ecliptic, if you could find a point in time where it's above the ecliptic here, then it makes it higher. So there are times that it's better to find this than others. So there's another challenge. You've got to hope that the moon is in the right place, the sky is clear, and it just by timing, it happens to work out well. So here's the geometry of the Earth-Moon system, and you can see here that at times the moon will be as high as 5 degrees further above the plane, and sometimes 5 below. So if it's below, it's going to be more challenging. And in fact, there was one that I was doing last year, and I was looking at it, and I went through and did the calculations, and it turns out it was so far below that it was basically almost setting the same time as the sun, and it should be setting so close to the sunset time, but it just happens to be the geometrics of the situation. So this 5 degrees is why there is an eclipse, a lunar eclipse and a solar eclipse every month. Just another diagram of basically the same. So there are times where it would be easier, if we're fortunate and it is above the ecliptic, it will be even easier to find. The name of my whole presentation was based upon a Sky Telescope article that I came across again in March 2016. It's called Seeking Super Thin Moons. And in it, they say that there are times that it's easy. Oh, let me try to get this. There are times like before dawn, if the moon is if the new moon is at this period of time or this period of time, you'll see 16 to 18 hour moon, or if it's within this period of time, it's a 21 to 24 hour old moon. Now, this is being videoed, right?
Yes.
Okay. So if you don't get a copy of the slide now, you can see it when it shows up on our website. So as a result, there are a number of periods of time in the upcoming year, April, August, October. These are moons that are periods of time that there'll be a thin, very thin crust, and it may be a good surge. So in a whole year, you'll get all of them. I've highlighted in blue here the 3 months that are best to see the moon at dusk, and the 3 months that are best to see the moon in the dawn. And seeking one at dusk and seeking one at dawn are quite a bit different. Okay, so what does Stan do? That he's going to go seek a young crescent moon. Well, I look at the time of the new moon, and then I go and determine what the sunset, sunrise times are. And then I'll kind of look at the numbers and say, will I have a reasonable opportunity? Because particularly when you're looking at one at dusk, there's a period of time that you've got to wait where you can't see because the sky is simply too bright. So there are periods of time that you can and cannot see these. So I've done this set of calculations for January. And there it is. So on the 24th, at 21:42 Universal Time, or 3:42 p.m. For us here, there's going to be a new moon. So obviously, if it's happening at 3, you won't see it that morning. So if you wanted to see it before the new moon period of time, you want to see the crescent, you won't see it at all. It's 8 hours. So that's what I referred to earlier, that, in that case, it's going to be 8 hours plus the day before. So you may be able to see a 32-hour-old moon. This one is a little bit difficult because the period of time between sunrise and between moonrise and sunrise in the morning is only a 35-minute difference. So that means that the sky's going to brighten very, very quickly. At sunset, you can see there that the calculation for sunset is 5:10. Moon sets at 6, so you got a 50-minute period of time. And this is what I would consider for beginners. This is a doable project. You can, within that 50 minutes, have sufficient time to find it. So this is what I'm suggesting for the beginners that you take an attempt at, a 26-hour-old moon. So it's good to practice what is this, because if you're going to be looking for an 18-hour moon, it's far more difficult. So it's easier if you do this when the moon is a little less challenging. You like that one, Paul? Yeah. So where I got all my numbers for sunrise and sunset is a lovely little phone app that Paul's always bugged me. There's a phone app for everything. So he's always got his pad out or his phone out, and he shows me this lovely little app. It's kind of nice. You go here and you adjust the date at the bottom here, and then it tells you the whole deal of sunrise, sunset, and all this. And then it even tells you how much of the sun is visible. It's a very nice little app, and you can flip through it, you can search months ahead, flip through it, and then work with the dynamics. Is it going to be good, or is it not going to be good? So this is what I used to get the numbers that I used, and it's available for Android or Apple phones. So then the next thing I do is I go to a planetarium program that I have, and I start taking a look and try to figure out where they will be placed in the sky. So I will plot the position of the sun at sunset, and in this case, it's going to be right about here, and figure out what the azimuth is. and then with the position of the moon, whether it be here or here, and then I'll plot it for every 5 minutes. So I line up with the chart something like this. And I know there's another person here who loves doing this as well, Bill Crosby, and I see him sitting way in the back. And a couple years ago, we had a real nice opportunity, and he actually sent out this information and said, hey, guys, this is happening, take a look. And unfortunately, clouds got in the way, but this is the kind of information you know. So we only need to know where the sun sets, because once it's below the horizon, we really don't care where it is. That sunset location is a marker. That's how we know where, when you see that, you'll know exactly, where the 246 degrees of azimuth is. So then what you want to know is, over time, what the height is and where the moon is, based on the azimuth and the altitude here. So you produce this little chart. Now, this chart is absolutely necessary if you're going to try to find this naked eye. So if you're going to go with naked eye, even as a beginner, one of the things that has been taught at some of the presentations here is how to figure out the degrees. So, you hold out your hand and you hold out a finger and there's a degree. You hold out a fist and there's 5 degrees. So knowing the location of where the sun set and using that as a marker, you can use your hand to basically figure out degrees. If you're using optical instruments, then knowing the width of the field of view, how big you're seeing in your binoculars or in your scope, that will allow you to know where it is. I'll get into that a little bit more. And if you're going to be trying to image it, you're going to want to find it early. So that's why I always do optically. And again, if you're going to try to image it, don't do these kind of challenges first time without having any knowledge, prior knowledge of what you have. You have to know your binoculars. You have to be comfortable with the way they work. You have to know your scope. You have to be comfortable with the way the scope works. You have to know your camera. Be comfortable with the way the camera works. We often have sessions where we show people the full moon and say, "Oh, you can take a picture." And people come up with their iPhone and say, "Oh, great! Can you tell me how to do this?" I say, "Well, hold it there, and it's not exposing correct." "Well, can you tell me how to correct the exposure for my phone?" "Well, I can't tell you because I use a different type of phone." So you've got to know your equipment to do this. So there's the equipment that I use, or example of equipment that I use. I'll have a pair of binoculars set up because they've got the widest field of view. This is just a picture. I've got binoculars better than this. I often are using the Celestron 15 by 70s. It has a 4-degree field. If I use a pair of 7 by 50 binoculars, just the typical binoculars, it's got a 7-degree field, so it's good to know that. And you want to put it on a tripod so that it's steady, and you want to put it on a tripod which moves nicely. If you have a tripod that everything's jerky, it really makes it difficult. I said in the previous slide that we do this sweeping motion, so you're going to want to be able to just move back and forth. So you want to have your equipment on a tripod, something like that. The other thing that I'd love to use is I've got one of these little Star Glass 6-inch Dobsonians. They're really nice little scopes, so I set it up on a table, get it off the ground. 6-inch f5, it's got a 30-inch focal length. If you use a 25mm eyepiece, it gives you about 30 power. If it's got a 50-degree field, it gives you almost a 2-degree field of view. So you've got to do that calculation ahead of time. You've got to know how to use your scope. And the thing with the Dobsonian is you're going to do the sweeping motion back and forth like this and that it's easy to use. Also, the fact that it's a 6-inch means you've got a large aperture. You're looking for something that's faint in a bright sky. This will help you. You may not see it with your naked eye. You'll see it first with the binoculars or the scope. And in Arizona, I've taken down an 8-inch f4 scope that I'm using for photography, and there's a couple of images taken with it here. And that's a nice scope too, because again, 32-inch focal length, a nice wide field, 32mm eyepiece will give you under 30 power. It's great. Other ways you could do it, you could use a go-to mount. Set the go-to mount to set it on the sun with a filter, and then have the go to the moon. I don't think that's part of the challenge. My challenge is to find one. So I don't really, I don't really like that idea. Another way is, if you are using a mount, and it's an equatorial mount, based upon where the sun is, you can set your setting circles and do setting circles. The same way you find objects in the night sky. You set the setting circles to a bright star, and you know something is so far away, and you can adjust the scope to where it is. The chart that you would make for this, though, wouldn't be one that tells you azimuth and altitude, but it'll tell you what the latitude, longitude of the sun was, and what the moon is, and then you know how to adjust the scope to find it at that location. Again, anytime you're doing something, and because I do mine at dusk, be careful, don't ever point a scope at the sun and use your eye. And then, here we go, we're going to start correcting. And we're going to check the weather and see. And if the weather is kind of, partly cloudy, then when you're going to the horizon, it's all cloudy. So this is something that gets wiped out more often than weather. So what you're going to need is relatively dark skies all the way down to the horizon here. And this is an interesting picture. I just picked this up off the web, and there's a crescent. And this happens to be Mercury. So in this case, you could use the crescent moon to find Mercury, or Mercury to find crescent moon. Now, I like to go and find a spot where the horizon is far away. You think, well, Stan, look how high the trees are. But this is taken with the telescope. So this is a 1-degree field of view. So these trees and such are less than a ½ degree of the horizon. So I'm trying to find something where I can see as far down to the horizon as possible. And such. And one of the things that you will notice when you're out there is you'll notice, okay, there's this higher ridge, there's a lower dip here, there's something in here. So if the sun came down here, these things become references on the ground. I used to take a bunch of my pictures on Brady Road, and then the province went and just off the south perimeter, and the province went and dug out that road, so now I have to find a new way to get there. It's a road where the no subdivision still above, so it's a nice place to do it. You could probably just go down Canada, south of the city, or there's many places if you go north of the city where you park off one of the major roadways, and you can find clear horizon all the way to the west and the east, depending on what you need. So then you're going to go out and you're going to set up your equipment. And you got to go out early enough, get your stuff going so that everything's ready and prepared. Because this becomes a racing tide. And like an eclipse, there's a saying about total solar eclipses, is that they only last 8 seconds. Once they start, it seems like time just blasts by. And even a 7-minute eclipse only lasts 7 seconds. So the same thing happens here. You get this time differential. So for seeking ones, during the evening at dusk, we're going to want to be set up so that we can determine where the sun is for our azimuth reference. Dawn chases are different. The moon will be rising. It'll be brightest at that point in time, although the atmosphere will kind of wipe out. So you're looking at it under different conditions where you're trying to find it before the sky gets bright. And you're trying to find it lower and then higher and higher. I'll get into that just a little bit more. So here's my carte du ciel. I took an image of it. And remember before I told you about that other picture that had Mercury in it? Guess what's going to be in the sky for this upcoming January? So with luck, you can find a very young, or very small but very faint Mercury to find the moon, or you could find the moon maybe first and then find Mercury afterwards. So I put these two things down here. Often there may be a building, a farmhouse, a telephone pole, a tower, anything that you can find, use as a reference. Could be trees of a sort, but we've got to nail down this position. That's where the sun, this is the sun ready to set, right at sunset, and there we go. We want to know where the 246.5 degrees is. This also shows, there's the ecliptic. So remember I was saying that, sometimes the moon will be below the ecliptic and sometimes above it. So in this case, because it's below it, it's actually lower. If it was on the ecliptic, it would be here. above it, but it would be there. So this is 5 degrees, so you could gain 2 degrees of height, make it even easier to fly. You don't have any control of that, unfortunately. So you get what you get, but you use that in the analysis. So then I'll watch exactly where the sun hits, and now I have my azimuth. So then you get excited, okay, I want to see it. But unfortunately, then you've got to wait. At dusk, the sky is so bright, there's not a chance you'll pick it up, not even with the large binoculars or the big scope. The sky is just too bright right after sunset. So you kind of wait. After about 15-20 minutes, I start scanning the horizon in the location that I expect it to be. And I'll show you that. And so this is, like I said, the field of view is a very important thing to know, and I use that to help determine where in the sky it will be. So this is 20 minutes after sunset. So it's still quite bright, but I know that this is the position of the moon here. This is where the sun set. This is my 4-degree field. So what you're going to do is, knowing where you had that reference point, you'll sweep towards where the moon should be. And this is an example of it. So, okay, that's a 4-degree field, so I've got to go over the 4, and there's another 4 to there. Okay, that will put it about in the middle, because that's 6 degrees difference. And then there's the 4 degrees there, and then it's a little bit more over 4, it's 5.5 degrees, around 6 degrees here. So then I'll scoop up there, and I'll be looking in this area. It's not that difficult to do. It's similar to doing star hopping when you're looking at the night sky, where you know something and you follow along. I use it this way because I like to follow along the horizon, so I remember, oh, there's a tree over here or something, so I know 1, 2, and then go up. Did I find it? No. Okay, I'll try that again. 1, 2, and then go up. Did I find it? Until I do find it. So here's about 30 minutes after sunset. And by this time, with the moon that's 26 hours, it should be visible. If the sky, if there's no clouds and nothing interfering with the brightness of the object, you should do it. You should be able to find it. And you should be able to find both these objects, in fact, at that time. Now I put down here a camera trick used for comets. Comets are the same thing. Often they're visible right after, sunset, and because they're following the sun as well, they're close to the sun. So you go looking for it. And one of the tricks is if you take a wider field lens, I talked about the photography of getting the moon, but if you take a wider field lens and you take a picture, often the camera will pick it up where you won't see it with your eye. So you take a picture, you look at the screen, is it there, is it there? So sometimes that will help you find it as well. So here's 5:50, moon set is at 6. By this time, the atmosphere is really starting to affect what you see. And I'm going to show you an example picture when I show a couple of my own images. It will really affect. By 5:50, you should have found it. The one thing is that with the 4-degree field of binoculars like this, you're just sweeping the horizon in that area. So this is what you should see if you go this January. That's about the right amount of crescent, about the right amount. The Cheshire Cat smile. So when you're searching at dawn, it's different because the whole dynamics are different. The moon is rising before the sun. So you don't have the sun going down as a reference point. So if you're going out, you should do what it takes in order to find reference points. If you're out, often I only see the morning ones because I've been up all night, and I've got a picture from Arizona to prove that. So you sort of know where the longitudes and latitudes are, so you can use that in order to help find it. When you do your binocular search, you're basically sweeping from the time that the moon is supposed to rise. You're sweeping a small area of sky with binoculars right along the edge, looking. And as time goes on, you'll know, okay, after about 20 minutes you haven't found it yet. Well, it's already should be, maybe it's 5 degrees above the horizon at this time. So you're adjusting where you're looking with your binoculars or where you're looking with your telescope. The problem is that as time goes by now you're getting the light from the morning sky brightening, and the differential between the brightness of the moon and the background sky is changing. You're losing the contrast. It's becoming far more difficult to find. So like I said before, I like to take images. Now that you found it, I thought I'd put a few guidelines. I like to take images. My real task is trying to get higher resolution images of this. So I'm shooting it with fairly substantial focal lengths. I find 400 millimeters for myself is a minimum that I like to use. Shoot up to 1,000 millimeters maximum, because then when you start getting it, you're trying to get something that's very faint, try finding it in a camera, and it's getting a very big field of view. So the pictures I've got are with 750 or 800 millimeter focal lengths. I'll give you an example of how much of the field of view in your camera it'll take up. If you've got a telescope that's got a motor drive, you can be using the equatorial telescope for this. That's even better because it's following along. Once you've got it nailed down, it's tracking. And that means you can take a lot of exposures in quick order, to get some sharp ones. Because you always get a lot of vibration and stuff in it. So I use an intervalometer, one of those devices, so I'm not physically touching the camera. In order to press the button on top, I'm using the electronic device that you can set your camera off, and then I know there's devices that you can put on the camera that'll trigger the camera, but you don't want to be touching anything if you can avoid it. If you're using a DSLR, I use the lock-up feature, and what that does is, you press the button twice actually. Before you take the first exposure, it takes the mirror, it lifts the mirror up. So now the mirror's not going to vibrate like this right before it takes the picture. So now the camera goes steady, then you take the second shot, and the whole thing should be steady. You can use things like a smartphone. If you're going to take a picture, then maybe what you want to do is a 2-second delay. So you set it off, take your hands off, give it a couple seconds to settle down, and click, there goes the picture. I typically shoot about 800 ISO, and to be honest with you, I could have gotten more into this, but imaging is the whole beginner's talk all on its own. So I'll give you those guidelines. And basically, there's 2 ways that I'm shooting, and I'm going to show you pictures from the 2 ways. This is called the afocal, where you're using the telescope. The telescope is focused with your eye. You found it. Oh, there it is. Then you can pull your camera up and put your camera up close to it. It could be, and I'll show you devices. There's handy devices now that you could just click onto an eyepiece with a smartphone camera. It's a nice little device here. This one has a clown, but this is just an older picture. They have them on. Mine has one. It's just got you clip it, put it on, let go, and it's holding on to the eyepiece, and there it is. And you will have the camera all set up to take the picture beforehand. Oh, practice. Don't try this. Don't try to do it the first time and say, okay, how's this going to work? What did Stan tell me? Whenever you do things like this, when you're doing a challenge, you're usually going to have some experience. So before the moon is that thin, try it ahead of time. Learn how to use your camera. The other way, and many of my images are prime focus. That's where you're just putting the camera on to your telescope and using your telescope as a telephoto lens. So the 2 systems I use, in one case a 750 millimeter focal length, in another case 800 millimeter focal length. So that's like having a big 800 millimeter f4 telephoto lens. And what you need for it is just a couple devices. You need a T-ring. This matches the type of camera that you have. And then this is the camera adapter, and this screws into there. And on a regular telescope, it'll fit in on this scope. It's slid into a huge adapter here. Okay, enough of that. So that's my challenge. I'm after something that's going to be 20 hours to 24 hours. What have I done to date? This is just, I only took images for my days of digital camera stuff. You'll see I don't have a lot of images because it is a hard thing to do. Often, skies are cloudy in the springtime, so it's a hard challenge. But there's one, and this is what I meant, that I'm trying to get images that, are relatively sharp. And I want to get them so sharp that you can see just the little dots at the end, just like you see like on the Terminator, where you see little pieces of the moon extending off the end. So there's a shot, 750 f5, 140 a second, a 23, 30-minute moon. So I've got under 24. So I'm into the category of very thin moons here. At that time, I was using that 6-inch telescope. I also took a picture. This is taken with a point-and-shoot camera, walking it up, holding it up to the eyepiece, and taking a picture through it that way. So it was a Canon A60 type point-and-shoot camera. I zoomed it a bit so that the circle, the big netting circle, because that is the lens of the eyepiece that I'm shooting through there, and there's a shot that I took that way. It's not as sharp as the other one, but it worked. So I caught it there. This is what the 8-inch f, the 800 millimeter, yeah, my 8-inch f4, 800 millimeter focal length. And this is, because it was I was shooting images all night, and then the camera's tilted relative to the horizon. So the horizon is this way. It is actually a mountain range in the distance. And just as it comes about, it gives me this crooked little smiley face. So I knew where to search for it, because I knew where the sky was relatively, and I looked for it, but it's so low on the horizon that in this case, the atmosphere just chewed it up, and you think, oh, that's horrible. So this is 22 hours and 48 minutes, so here's sub 23 hours. And that looks terrible. But I just kept shooting and shooting and shooting, and 6 minutes later, it looked a whole lot better. It's still just a little bit funny here, but so there's the moon. Again, no details. If you want to see details on the moon and find out what they are, you'll need to come to the beginner's talk next one. And then there's another one. This is the portal. This one I'm shooting. It's on the other side. And unfortunately, because of the timing of when the new moon was, it was, you know, the 9.5 hours plus the 24. So this is just a thin crescent moon. The thing I liked about this one is that these two were tied to the same new moon. So I got a shot of the image of the very thin crescent before the new moon, and a shot of the crescent right after the new moon. And that's about 60 hours apart. That's what I do for fun. So this is a shot, so I mentioned it, and I mentioned earlier that Bill Crosby, one of our counselors, also likes to do this. Now, is it easy for you guys to see the moon? It should be right here. It's just got, it shows up. Oh yeah, easy visible here. It's right in here. It's right there. Can you actually see it? I don't know if you can. It is tough. See, I told you they were difficult. And underneath here, I don't know if you can see, but over here is where Mercury was. So Bill had a nice picture that he took with a 200 millimeter lens. Details are there. Moon only 3 degrees above the horizon. I love that. Again, 22, 29 minutes. So you beat me by a minute, Bill. Mine was 22, 30 minutes, I believe. So that's the thin crescent and a couple of planets visible. And as Bill says here, and I'm going to read this, what was cool at the time, the fact that Venus was 1 degree to the left of the moon and Mercury was 1 degree directly below. So this is a challenge. This is something very difficult to do. And because there are so few times you have the opportunity to do them, this is a challenge you can take with you for a long, long time. And I've been doing this for 30 years. I've got some pictures on film. This one was taken on film as well. So what's up? I'm going to continue to seek out thinner and thinner crescents. I've got my current record. I'm going to keep trying to beat it. Weather keeps beating me. But my goal is to find a super thin one, something that's in that 16 to 20 hour range. And that's my presentation. Any questions?
I have one. Have you ever thought of using polarizers to assist you in healing the sky glow?
I have.
Very effective.
I have.
Very effective. You should
So would you use it visually? Did everybody hear the question?
No.
Oh,
It's
sorry.
asking if I've ever tried using polarizer filters.
Yeah, polarizer filters, that's right. Yeah, I use them routinely with my binoculars, and it makes a huge difference. I've even seen a sub-24-hour moon. Oh, sorry. I've even seen a sub-24-hour moon mid-morning before it got really bright. The sun was already up, but I was waiting for the sun. You can still see it with higher power. Not my 2500s, but my standing image stabilized. It's really possible. So you might want to try that.
Okay, there's another helpful thing. Any other questions? Go ahead.
I suggest you turn off the stabilizer on your camera before you take the pictures, because it takes a fraction of a second for a stabilizer to stabilize, and in the meantime it's taken the picture and you get a little bit of a smear on it. Because the crescent's so small, the stabilizer doesn't grab it right away the way it would on a normal scene. I've ruined many a lunar picture by leaving a stabilizer on.
So everybody caught that? So on your DSLR, on the lens itself, if it's an IS type of image stabilizer type of lens, turn off that function. Any more questions? Is anybody out here actually interested in now trying this? It's actually it's a very fun thing to do. The C1 is, you get a nice feeling of accomplishment when you finally do C1, because it's a challenge, particularly because of the weather and where we're located. Okay, thanks.
If I get like a thin moon there, it has to stay there.
Testing, okay.
Well, I can personally vouch for Stan that he's not a morning person. I was with him in Arizona a couple of times. All right, so we have quite a lineup. My name is Brian Stach. I'm the club president. I'm also the director of Plan Lead. And we have quite a lineup today. So let's get it started. Hopefully we have enough time to cover it. One of the things that we have to cover today is the election. And I'm happy to say that everyone wants to come back to it. Let's start off with the open house of University of Manitoba. Unfortunately, the planetarium's not ready, right?
Not quite yet.
Not quite ready. Okay. So, January 29th, I didn't put down. Okay, it's 7 o'clock, right?
Yes.
Okay, sorry, I didn't put the time down, but so I'll be there. Old Comic Marsh, again at 7 o'clock. And what do I have? January the 16th. So if you have a telescope, you're free not to pay the $10 fee for it. It gets waiver if you are a RASC member. So it's another good attempt to do more astronomy with your fellow members. Okay, sorry. I'm a little off today. I had a long day. Potluck is coming up, January 18th. Sean, I think you're here, right? Yes, he mentioned about the hot tub. Did I put that down? No, I didn't. So you have...
Bring your suits.
Bring suits, okay, and there's going to be a hot tub there for anyone. So I'm looking forward to it, but he did say that he wouldn't mind people to RSVP him at this email address for him, because he wants to know how many people are going to be coming down. All right, of course, this product is a really good time to spend some quality time with your members. I just threw this in here, I wasn't too sure, but I think we're almost completing testing of the web page. We're almost up and running. We should be in the final stages and should be ready in a couple of weeks, hopefully. One of the things that we're trying to test out is the forum. And I think Sylvia was here, and I think Sheila, right? We're all testing the forums right now. And the goal is we use the forum on the website. It also should mirror the one that we're currently using as the email list. So if you use one or the other, and of course we have the Facebook account that we're, thanks to Scott Young, that we have. I'm still getting used to it. I haven't really posted much about it, but it's nice. Okay, Explore the universe. Dennis, you're here, right? Thank you. So if you want to explore the universe, it's a great way to get to know the skies if you're a beginner. I read that 55 objects, you only need to do the 55 objects. It's a great way to know the sky. If you want to learn more about it, talk to Dennis at the break. We do have a telescope loan. Abdul is the person who is in charge of it. Abdul, do you want to say anything about it? Do we have anything?
Like we have the three of them actually.
We have three?
Yeah.
Okay, so you want to talk to them at the break, please do. The elections, this is something that I have to go through today. We do have three openings, two councils and the vice president. But I'm happy to say that these people are up for re-elections. So, as Brendan has pointed out to me, I have to go through the formalities of it. So, what I have to say is, do we have any nominations for these positions? We'll start off with the vice president. So, is there any nominations for the vice president? Going once? Going twice? All right. Dennis, you're back in. Thank you. But unfortunately, you turned 2 years. All right, so it's 2 years, not 1 year now. Okay, now we have two other positions that's open, the council. Again, we have two openings, Darren and Ed. So they're up for re-elections. So again, is there any nominations for the council position? Going once? Going twice? All right. That's it. Okay, Darren and Ed, welcome back. So the council hasn't changed one bit. All right, that's great. So that was painless. All right, welcome back, guys. All right, so Glen Lee Observatory, that's me, the director of Glen Lee. We're not going to have new members night tomorrow night. Frankly, I think it's going to be way too cold to do it. But we'll just keep it brief. One of the things, we'll probably have it next Saturday. We'll see how the weather is. But of course, for some of the new members, I'm welcome to show you how to use the Glen Lee, the LX200. And of course, some of you may know that we do have a remote control from the warm room. So you have the ability to control the dome and the LX200 from the warm room. I'll be happy to show you how to do that. All right. So I said it was canceled, so we'll move on to our next presentation of What's Up with Jay Anderson.
What's up?
What's up, February? What's up? Everybody's going to stay in bed. Well, the sun is kind of interesting right now. We have a sunspot on it, although as you can see it's on the upper right and it's about to disappear over the edge of the sun in the next day or two. What's interesting about it is that that sunspot is part of the new solar cycle that's beginning. And one of the ways you can see that is it's very high latitude on the sun. Whereas the old solar cycle, this one here, is coming to an end, and any sunspots associated with that would be lower down, closer towards the equator. So you can see, here's the way the sunspot count has been coming, and this is the predicted count. This came out last month, about a month ago. And what's interesting about this, they're indicating a minimum in April of this year, plus or minus 6 months, which is about 1 year ahead of what the previous prediction is. So they're putting an end to the current sunspot cycle and beginning of the next one a year earlier than what. Here's the actual more detailed sunspot count. You can see it's still got the old predicted track on it, it carries it out for actually into 2023 almost. So a little bit of an encouragement, I guess, for those of us who are waiting for the sunspot count to get up in here, and the amount of aurora will gradually increase. In the bottom line, I'm showing the cosmic ray flux. That's sort of anti-correlated. The lower the sunspot cycle, the higher the number of, or the flux, the rate of incoming cosmic rays. That's because when the sun is active, its magnetic field slows down and diverts cosmic rays from striking the Earth. And take a look at what the sky is like in the evening, greatly enhanced with the aid of planetarium program. And you can see that the winter Milky Way here at 9 something in the evening is more or less stretching straight up from the southeast. And the ecliptic, which is the path of the sun, although there's no sun in it, but the moon's following along close to Uranus and Neptune over in here. Neptune's about to set in the west here. Uranus is going to be up high for the month. And we can see that the winter constellations are just rising, Leo in particular, and behind it, Virgo. I wanted to sort of make some comment about what's visible in the sky. Of course, move the point of view a little farther over, so now the Milky Way is down on this side. And you see these little circles in here. These are typically mostly open clusters, and some globular clusters in there, and some planetary nebula. But there's none of those little circles out in here. Instead, we get these little dots here. When you're looking toward the Milky Way, all of the dust and gas in the Milky Way blocks anything that's behind it. But when you look away from the Milky Way, you start to see this stuff that's farther out. And all of these are galaxies. And you can see the Virgo cluster of galaxies in here. There's a little cluster in Leo as well. You can point a telescope anywhere in that area, and then that area is several times, 5 to 8 times the size of the full moon. And you can put a telescope anywhere in there, you'll start seeing galaxies. This is only a small number of the thousands that are in that region. So if you want to try your hand at galaxy hunting, you won't be able to do it with binoculars, but if you get out to Glenley telescope and turn it on one night and open up the dome and park it in that region, you'll get yourself a real treat. And some of those galaxies are pretty bright as well. We get into the current planets. Mercury is in conjunction with the sun, so it's not visible at the moment, but it's coming out once we get into February, and will be placed low in the evening, but because the ecliptic is at a low angle and not a sharp angle with the horizon, when Mercury comes out from the sun, it's going to stay low down. So it'll be bright and it'll be visible, but you'll have to look for a little bit with binoculars. Venus, of course, you probably all saw that on the way in today. It's going to be getting brighter and brighter. In fact, it's not very big, 17 arc seconds in size right now, but when it gets to June, it will be up to 52 arc seconds in size. If you're under the age of 20 and you have good eyesight, you should be able to see Venus as a very thin crescent, and Stan will be leading expeditions for photographing the very thin crescent of Venus, which you'll be able to do quite comfortably in summer skies at pleasant temperatures. And it's so bright you don't have to look for it. So Venus is going to be a real treat, and Mars is going to be a little bit of a treat, but it's going to be October before Mars reaches opposition. It's going to be one of the closest approaches of Mars until the 2030s. So we should be able to get, as we get into the late summer and fall, some very nice views of Mars with the Glenley telescope or any other substantial telescope. When Mars is at its maximum size, though, it'll be above 17 arc seconds, so it's not going to get as big as a full moon, despite what you're going to read on the internet when it comes along. I wanted to show you a diagram of where the planets are when you look down on the solar system. This is the inner solar system, Mercury, Venus, Earth, and Mars here. So from Earth's point of view, if you're on this side of it, you're looking in toward the sun. And so you you can sort of draw these angles. So this line here is a line toward the sun. And if you're standing on the Earth, you assume that big circle, the Earth is turning in that direction, also moving in that direction. Then you're going to be overhead. And so as you turn with the Earth, the first thing that's going to disappear over here is the sun's going to disappear. You'll still be able to see Venus. Mercury is over here behind the sun, so you're not going to see it. So what this tells you is that Venus is in the evening sky at a certain angular separation from the sun. Mars, on the other hand, is on the other side of the sun, so if you're on the night side here turning toward morning, first you see Mars before you see the sun. And so Mars rises before the sun does in the morning. And we take a look at that a month from now. The Earth has moved in its orbit, Venus has moved in its orbit, Mercury has now come out from behind the sun, and Mars has also scooted along a little bit, but not very much. We do our angles again. We now see with the angle toward the sun, and again, as you're turning, the first thing that disappears off the horizon is the sun. You can still see Mercury and Venus, and Mercury and Venus will be together in the evening sky at that point, although Mercury will be quite a bit closer to the sun. It won't be very much above the horizon. Also, because Venus is moving more quickly than the Earth, it's caught up with us. So Venus is at a closer distance to us than it was previously, and now it's also at a much larger angle away from the sun. So to you, that would mean that Venus is getting higher in the sky in the evening as it gets farther away from the sun. At the same time, Mars is doing its own trick. It's moving fairly slowly, so you won't notice too much of change in Mars. We get into the other planets farther out from the Earth. Jupiter is in conjunction on the 27th, so it will be coming up in the morning sky, although it hasn't started to do much right now. Because the ecliptic is low, it's not going to be very prominent for the next month. And Saturn is moving toward conjunction in 3 more days, so pretty much write it off for the next month. But Uranus and Neptune, as you saw in the star chart I showed you, are fairly high up. Uranus is visible through the month, fairly high, over 50-odd degrees in the southeast, southwest, and Neptune is up at 26, but it's going down toward the sun, and it's going to be pretty much invisible by the time we get to the end of the month. Just take a look at the charts here. I'm only showing you one of them, but what we have here is the Earth. In this case, we have to look sort of skim past the sun to see Jupiter and Saturn in the same direction. So as they move in their orbit like this, and the Earth moves in its, they're going to be shadowed or hidden by the sun. But because the Earth is moving more quickly than they are, we're going to come around to this side and get a better view of them, even though they're only going to move very small distances in the next couple of months. So they'll be getting more and more visible. It's essentially the motion of the Earth that's controlling the visibility of those planets, not the planets' motion themselves. Pretty picture, crescent moon in the morning. Stan will be leading that as well. Well, it's probably a little more than his 20-hour because what we want to see here is with Mars in the morning. This is interesting. Neptune and Venus are very close to each other. Might be a good opportunity to see Venus with a small telescope or higher-powered binoculars. Sorry about Neptune. Neptune's about 8.5 magnitude, though, so it's really not a binocular target unless you're pretty skilled. We get the crescent moon passing under Venus fairly far, so it's not particularly interesting. Just for the record, January 28th is on average our coldest day of the year with an average low of -28. So when the CBC tells you it's frigid -28 tomorrow morning, hey, that's normal. February 5 to 9, Mercury and Venus are together in the evening sky. They're fairly low down, but that's when Mercury has come out to the position I showed you from around the sun. So it'll be low down, Venus will be high, but the pair of them should make a nice little picture. And of course our zodiacal light, which is the reflection of sunlight off of dust on the plane of the Earth's orbit. It looks like a cone of light sticking up from the horizon. It starts to become prominent in February, but March is really when it'll get to its best. We have Comet. When we talked about last month, Comet Pan-STAR must be Pan-STAR 127 or something like that. But it's forecast to come up to about magnitude 8. These are recent magnitude estimates. So it's getting close to its peak, which will come in June. So it's slow moving. What's interesting about Pan-STARs, here's a picture from Europe from December. What's interesting about Pan-STARs is right now is up in this part of the sky. This is a double cluster in Perseus. Cassiopeia is over here, Perseus is over here. And the motion of the planet is toward, from its position today, going to sweep down this way. Here's the double cluster. So in around February 3 to 5, it's going to pass the double cluster. Make a very, very nice photograph in that area with the double cluster that comes in it. And then for those of you who are willing to tackle the weather 10 days after a supposed lowest temperature. Other two interesting events, I haven't talked too much about these. Asteroid occultation. And that's when an asteroid passes in front of a star, and it's like an eclipse of the star. If you've never seen one, then you probably just want to watch one. But you can see the track, the projected shadow of this particular star across the Earth takes it just about right over top of Winnipeg. There are the things. So it's a fairly faint star, 11.7 magnitude. You need the Glenley telescope to see it. And it's expected that the star will disappear for 5 seconds or thereabouts as the asteroid goes in front of it. If you're really sophisticated, then you videotape it and time it very accurately and send the results in to the International Occultation Timing Association. And they use it to calculate the size of the asteroid according to the length of time it blinks out as it occults the star. This is January 23. What's interesting is the same night, and in fact an hour and a half later, a second asteroid passes over the city, again with an 11.7 magnitude star, this time a 3.5 second or so drop. Fairly substantial drop in magnitude, so 11.7 will drop down to almost 15th magnitude, which would essentially make it invisible. So that night out at Glenley with a big telescope could be interesting for somebody who wants to videotape it or just watch it and maybe do a rudimentary timing. We used to do this quite a bit in the RASC Center here. It's fallen by the wayside over the past few years. It's a lot cheaper to send a satellite to it for $1.5 billion. And so there we are, up to the cap. Thank you very much.
Okay, Michelle, you're next.
Okay, so today's what's new. I'm actually going to work myself from way, way out to way, way in. So the first slide is dark matter may be cold. Basically, there's a recent experiment that looked at quasars through a Hubble Space Telescope. And through a method of gravitational lensing, they've actually detected small sized clumps of dark matter, much smaller than normal. You can see here's a picture of the Milky Way and the typical size of a dark matter clump or a small clump. And these clumps are 1/10,000th to 1/100,000th of the Milky Way clump. And this was observed for 7 quasars. Talked about gravitational lensing before, but here's a little reminder picture. So you have a quasar in the background and a dense galaxy with dark matter, it will gravitationally lens the object. And in this particular case, these quasars are almost in direct line of sight with the source. And you get these 4 star patterns from the lensing. You see that through the telescope. So there's 6 examples here showing the gravitational lensing. And so what they do is they model this, and they try to subtract out the dark matter. And what they've discovered is it's clumpy. And what that means for, there's different kinds of dark matter. I had talked about before. There's cold dark matter, hot dark matter, warm dark matter, and they're all, have different properties. So this is just sort of a quick reminder, but this is all dark matter stuff, candidates you can find, and you can spend forever researching all these things. There's a Nature article here on this, and these are my picks for cold dark matter. Neutralinos. I like neutralinos because it combines our regular knowledge of particle physics with standard knowledge of particle physics and supports things such as superstrings and stuff like that, which is superstrings and membranes at the moment are the only viable theories of, that unify particle physics and gravity. The problem is they predict things we haven't seen, so until something happens, it's just science fiction. Then axions is my next pick. Usually when there's a symmetry, you'll find a fundamental particle, and in this case it's a quantum chromodynamics. There's a charge parity symmetry, and they're expecting to find some kind of particle, but haven't seen it. And sterile neutrinos. So basically, I guess what they're saying here is you form these cold lumps, and these type of particles are candidates that have the potential for doing it. It doesn't necessarily rule out everything, but at the moment that's what these experiments seem to indicate. The LIGO array picked up another neutron star merger, neutron-neutron star merger, and this is the second one that is done. The first ever detected was back in 2017. It used 3 LIGO telescopes as an array, and you can see there's a Virgo and 2 here in North America. And this array can be used to sort of triangulate or swap the sky, and then they can train optical telescopes onto it to see if you can find an optical counterpart. And I think it was a Hubble picture here, but I just put in swoop in Magellan, so you can see this little spot here in this region, and that's the evidence of the supernova. So unfortunately, this one that they detected just back in April 2019, only one telescope detected it, so we won't actually be able to triangulate it because it's like it could be anywhere, and so there's no optical counterparts to it. It's the total mass of this one is the massive one yet, but of course there's only 2, so and it's about 3.4 solar masses, so it's likely formed into a black hole. So I just presented this one. So you have an idea, and I put up this video, which, yeah, there we go. So this shows an animation of that particular one that they saw. There's the 2 neutron stars, and this is them colliding. So this is a simulated model. The NASA website has, I like the NASA website because they have a lot of, they have a lot of videos that you can download and use for educational purposes. Quite often, if you see them on YouTube, you can usually find them on things that you download. So we talked once that a galaxy had a warp, I mentioned that before, but this is a different kind of warp. So basically, Gaia is a large survey, and they And so they'll have to rethink their models of galactic structure and evolution. So it used to be, they used to think of it as Gould's belt, which was sort of went around the Earth, as our sun. And now it's maybe a Radcliffe wave, and it might still be part of a galactic arm, but it's a weird thing. So we got away from out there, and TESS, which is a transiting exploratory survey satellite, picked up the first Earth-sized. It's designed to look for Earth-sized planets, exoplanets, and it picked up the first one. There's been other detectors, I should say, but this particular detector picked up its first one, which is about 100 light years away from Earth, and it's within the habitable zone, but the star is a red dwarf, which is much lighter than our sun. So the habitable zone is even and less dimmer and dimmer, and so the habitable zone is closer to this star. So there's two problems with that. Red dwarfs, they live a long time, but they do get a lot of solar flares, and so there's a lot of events that are hazardous to light. And because the planet is so close, it can become tidally locked. So they strongly suspect it's tidally locked. They've observed it for about 11 months and seen no flares. These flares can happen every couple of minutes or something like that. So they think it might be stable. So there might be a chance there might be life on it. So there's some debate about that. But tidal locking, not sure what kind of luck we have in a tidally locked planet.
Can I ask a question?
Sure.
How likely is that a solar flare can affect life?
Sorry, I can't quite hear you.
Yeah, so you mentioned that the red dwarf has solar flares,
Right.
and that the planet is already closer to the red dwarf to be in the habitable zone.
Right.
So the question is, what is the impact that a solar flare from a red dwarf could have in the development of life?
Well, okay, well, let's look at our solar flares. We had one event, wasn't it recently? Just knocked out the entire power grid across Ontario and parts of the U.S. Yeah, and that was just from highly charged particles coming towards us. Solar flares, depending on the atmosphere and everything else, can penetrate the atmosphere. In fact, when you look at aurora and stuff like that, that's from solar activity. Now, of course, the solar flares coming from our sun are quite small, and we do have a solar expert here, so I don't know what the size of those are, but I would imagine that there's a lot more particles coming out and can be hazardous. It's like being exposed to a lot of radiation. That being said, who knows, there might be life that can withstand, that's adapted to withstand higher radiation environments. I mean, if we had, it's like, for instance, weeds and cockroaches would survive, so we could send them there. But, so yeah, there are things that can survive, so who knows? Would you know how big the events are for these things?
It's thought that magnetic activity or space weather around the red dwarf is significantly stronger than it is around the sun, and the intensity of the magnetic field, which tends to dictate how strong these events are, falls off as 1 over the distance squared, roughly. And so for a habitable zone that's a lot closer to that star, the magnetic field is going to be a lot stronger, and so it'll have a larger effect. The other thing that might be worrisome is that our Earth is protected by from a lot of these magnetic storms by our own magnetic field, and in a tidally locked planet, it won't be rotating fast enough probably to generate a magnetic field, so it won't have that protective layer. So both of those things together make it less likely that life will be.
Unless it's like Neptune on its side.
Yeah.
Yeah, but it's interesting, the reason we're here, there's a lot of little happy coincidences that we're here. Jupiter is one of them. Our Earth's magnetic field is another, and the moon keeps the Earth stable, because otherwise the moon could flip over and point to the sun, and you have like a super summer and super winters. So there's a lot of little happy circumstances that has allowed us to evolve. And so it's a very stable system. It has to be stable for a long, long time for that to happen. So it's interesting, red dwarfs are around for a long, long time, but in the habitable zone, it's not conducive to life. But if it were, there could be highly advanced civilizations living around such stars because it could have a lot of time. Okay, and then so now we've gotten way out there to the moon, and this is just a little synopsis of Tian 4 year-end review of this rover, which has been one of the first rover to go to the dark side of the moon, and it's exploring the South Pole. Danielle has given a talk about the moon and the South Pole, and it's picked up evidence that, yes, there's stuff at the South Pole that's come from the inner core. But when I read through this article, one of the more things that struck my interest more is that they have a whole series of these probes they want to send, even a return probe in 2024. And what they're really looking for is a viability for a moon base or outpost. And it's believed there's water ice, well, it's been shown there's water ice at the pole, so they want to know the nature of that. And of course, they wouldn't be doing it alone. I believe there's some joint plans between the European Space Agency and American Space Agency, whatnot. So, quite interesting. And finally, the end. Yes.
Could satellite galaxies with large and small Magellanic Cloud be influencing this warp at all of the galaxy?
I don't know.
Could you repeat the question?
It was asking about the satellite galaxies, such as the LMC, whether they would influence this. I think it's more. I'm currently kind of studying galaxy evolution, and like, for instance, as we go around our galaxy, our sun bobs up and down through the galaxy and does these weird cycles through the galaxy. So it could be that it's part of this natural dynamics. And whenever you look at a galaxy, you see the main arms, and what happens is at the front of the arms, the gas gets compressed, and at the back, so you get star forming at the front of the arms, because that's where the gas gets compressed, and then the stars bleed off into the back. So it could just be a natural part of galactic dynamics. We have to modify our models. That's my suspicion. If I were to hypothesize anything to do with the satellite galaxies, maybe it has something to do with that tilt in the middle. That might be a more logical explanation. Any other questions? I'm just hypothesizing here, of course.
We have a very special guest here, Scott Young from the Planetarium. He has something to say. Yes.
Yeah, that was great. Hi, everybody. This is the first time I've been here in quite a while. It's nice to see you all again. I wanted to tell you about a couple of things that are coming up, and I called it What's Up at the Planetarium, but you already have somebody doing What's Up. So I went to What's New at the Planetarium, but you already have somebody doing What's New. So this is What's On at the Planetarium. And of course, this is a pretty exciting time in astronomy, and we've got a couple of programs that I thought some RASC folks might be interested in. The planetarium I'm speaking of course, is the one downtown at the formerly the Manitoba Museum of Man and Nature. Now we're just the Manitoba Museum, and that's the view out of my office. The planetarium is a 60-foot or 18.3 meter dome, and it's got this lovely Zeiss star machine in it named Marvin. Did anybody go to the planetarium when it opened in like the late 60s? Does anybody, okay, is it Marvin the paranoid android from Hitchhiker's Guide, or is it Marvin the Martian from Bugs Bunny?
Bugs Bunny.
Okay, is that the votes, or is that the actual? I think it's Bugs Bunny too, yeah.
67, the Hitchhiker's hadn't been written yet.
That's right, because I was like, okay, perfect. Thank you. There was a debate earlier. Now Marvin is our optical mechanical piece of wizardry to make the stars. But the problem with Marvin, he makes a great sky, but if you want to show anything else, some of the dark matter that Michelle was just talking about or things like that, Marvin doesn't have a dark matter lens. All it does is show the sky from the Earth. And so we have another system which is called Digistar, which is basically all the rest of astronomical knowledge in a simulator that we can then portray up onto the dome. And so the two of those work well together. Coming up, we have a special event which is called Dark Matters. And actually this is based on an event that we ran with Dr. Michelle Boyce last year when we had a nice party at the planetarium and sat around with a glass of wine and saw a planetarium show, and then she talked about dark matter and dark energy and all that cool stuff. It was so popular we decided to turn it into a series. And so the Dark Matter series has two events coming up. January 30th, we have this guy, Dr. James Peebles, who did his undergrad degree here at the University of Manitoba, was born in St. Boniface, then went on to work at a small independent university in New Jersey called Princeton, and he picked up some prize just recently, the Nobel Prize for Physics 2019. He unfortunately doesn't travel, but he will be basically doing a live video conference into the show, and we'll be doing a planetarium show. We'll chat with Jim. He'll tell us a little bit about his work and things like that, and then we'll have wine. So that's coming up. We're also running an Introduction to Skywatching course. This is something that actually Bill Crosby, I heard, is Bill back there somewhere? Bill used to teach this course back when I was a kid. So we've been running it on and off ever since then, and that's starting up in January. So if you're brand new and you want to learn where the constellations are and spend some time in the planetarium and get to know the sky without having to worry about the weather and the clouds that Stan was pointing out, sign up for that. And we have two great shows that are running right now. One is The Search for Life, Are We Alone? This is written by, how many people saw Cosmos, the Carl Sagan version, the original? Yeah, okay, so Carl and Stephen Soder and, geez, I forget her name, Annie Dringen wrote that series. Carl was the face of that. Those two writers wrote this show, and it's narrated by Harrison Ford. Really, really good show. So that's running through March. And then if you're into something a little bit more, I won't say simple, but certainly a little bit more jazzy, we have the Zula Patrol from PBS, and they're doing a great little show which is all about the Earth. And as you can see, they get chased down by dinosaurs and flying saucers and things like that. It's actually a fun little experience for kids, and it's a nice introduction to the planetarium in sort of a TV kind of format. So the planetarium is available to you. We'd love to see folks out. We'll have to have another meeting there sometime. It's nice to have folks down. And yeah, that's about all I have right now. And we're looking forward very much to seeing the second planetarium open up. So we have colleagues. It's going to be great. Any questions? Cool. It's great to be back. Thanks. I forgot. A draw for 2 pairs of free tickets to the Jim Peebles talk. So to win, to qualify to win, you have to email me at skyinfo@manitobamuseum.ca. That's SKYINFO. We'll send this out in the email list as well. And you have to tell me your earliest planetarium memory. It doesn't have to be my planetarium. It can be any planetarium, or you haven't been there yet and you'd like to. Send me a story, and from all the entries, we will draw a couple of names, and we will send out some free tickets.
Thank you, Scott. We're going to try something new. Gail, we're going to try to use recycled cups.
So yeah, just I brought 15 cups, reusable cups for tonight, and we'll bring some more later. So I thought, you know, if you can use reusable cups, it'll be a small contribution that we can do for the environment at the RASC. And and if you have some of these, by the way, these Tupperware old school cups, and you want to donate them, bring them over, and I'll take care of them, bringing them to the meeting. When you're done with your cup, no rush. You just drop it off in this pail. It'll be by the chair there. So that's it.
Hey, thank you, Sylvia. Bill Ferguson, are you here? Who? Okay. All right. Need a 9 o'clock.
Is that yours, or? Oh, is it yours? Okay. It was left here at the entrance? That was yours, okay.
I read a book called Who's fascinating?
Okay, so starting with the lateral half of our meeting. I'm pleased to announce that he's second time around, Dr. Bill Ferguson. You know, he's a lot of members has won him back, so here he is. This is other presentation. So, all right, thank you.
All right, how's that? Sounds pretty good? Yeah. Excellent. Well, so I'm thrilled to be back here again today. I had a great time when I was here last year. I was asked if I could come and say something today about my research. So I think I probably met many of you when I was here last year, but in case you don't know who I am, my name is Phil Ferguson. I'm a professor of aerospace engineering or mechanical engineering here at the University of Manitoba. I started here in about 2017, and before that I worked for about 10 or 15 years on many of Canada's space programs, so many of our missions, including RADARSAT Constellation mission, which we just we launched this year. All 3 satellites are in orbit and performing really, really well. I've worked on the MOST microsatellite and the NEOSat microsatellite, as well as some of the big space robotics that we see on the space station these days. But what I'm going to talk about today, I was asked if I could come back and maybe say something about the research that I do here at the University of Manitoba. And so my area of research is in spacecraft guidance, navigation, and control. And so when I thought about kind of what I did and how it might overlap with some of the interests in this group, I thought, you know, this might be kind of an interesting opportunity to talk about how we use stars and space telescopes to navigate in space. But when people ask me, they say, hey, Phil, that's really cool. You're a rocket scientist, you know, you do space research. You know, what's the coolest part about your job? I say, well, the coolest part is I kind of get to pretend like I'm on CSI, right? So my job, I see I'm almost kind of like a detective, right? So when we do space navigation, we do something, the fancy way of calling it is multi-sensor data fusion. But really what that is trying to extract interesting bits of information out of what would be probably a really simple measurement, right? So I mean, we've all watched CSI, and you know, we've seen these people that are crawling around on the ground looking for clues, you know, like shell casings or a little bit of blood or maybe some pocket lint from somebody that might have a little bit of DNA on it. And so you know, what they're really doing, I mean, that's what I think they're doing, is they're running a filter. They're running a filter in their head. They're finding little bits of information, and what might look like something sort of innocuous to an untrained eye, the trained spy or the forensics analysis sees something very, very different. So, so for instance, if you and I were to just see a red car driving down the street, that might not mean anything to us, other than, well, maybe that person likes red. Right? But to somebody that might be, say, an insurance adjuster, they see a red car and they think, ooh, money, money, money. People that drive red cars tend to get in more accidents, so I'm going to charge them more for their insurance, right? Now, by the same token, if I see a red bird, then, maybe I'm excited because it's a nice-looking bird. It's a cardinal, right? But if I'm, say, lost and I'm somewhere in the world and I see a red bird and I know something about where that red bird lives, that might tell me something about where I am right now. If that red bird was something different like this, then it might tell me something, again, very different. And it's probably something that my kid shouldn't be doing, and instead they should be doing their homework. But the whole point here is that what we're trying to do in this field of study is pull information out of measurements. And how much information can we get from a measurement if we kind of squint at it and hold it just right? Sometimes I think of this as kind of getting water from a stone, right? I once, when I was doing my graduate work, we had an in-house statistician. His name was Alan Nadapoff. And he was a great guy to talk to. And he always used to say that any bit of data should be able to generate at least 5 or 6 PhDs. Right? And now he's talking about entire data sets. But what we think of when we talk about data fusion, I think one little tiny piece of data, whether it's a measurement of a star or it's a time measurement of something, you should be able to get a lot of really interesting information out of it. And the field of multi-sensor data fusion is really just that, trying to maximize the data return. So I like to stop and think every now and then, okay, well, what are the kinds of measurements that we typically have available to us, right? And so physics certainly kind of dictates saying, well, we have length measurements, we have time measurements, and we have mass measurements, right? And sometimes that length measurement isn't a length measurement, maybe it's an angle measurement. But pretty much everything else that we measure is a derivative of these. Now, I will give you that you could argue that maybe you could measure velocity directly through Doppler measurements, but I'd argue that that's more of a time measurement than a direct velocity measurement also. But the problem is that oftentimes when we're trying to measure, we can't measure directly. We have to measure something and infer it from that measurement, much like the game Clue, right? So we're trying to find out who done it, right? And oftentimes you can't go up to Colonel Mustard and just say, hey, Colonel Mustard, did you do it? Right? No, we have to find out the clues. We have to say, you did it. You did something in the parlor, and I'm pretty sure it had something to do with the candlestick holder. And then you infer that probably it was Colonel Mustard, in the parlor with the candlestick holder. Right? But in space, not only is it not possible to ask space what's going on, it's absolutely not possible for us to take direct measurements of the spacecraft if we want to find out where it is and where it's pointing. So that then leads us to the question, well, how do we navigate in space? What are the tools available to us? And how can we make this better? How can we grow in space to be better at navigating? So I thought I'd just take a little bit of time to just walk through some of the basic sensors, but I'm going to focus on one in particular. So sun sensors, that's a pretty good one. I mean, if we can see the sun, and we know the sun is over this way, that must mean we're pointing over this way, right? But we would have to know something about where the sun should be. So another option is to use, say, a magnetometer, like a compass in space. We use these very often. And that they can tell us, well, what direction are we pointing based on what direction we think the magnetic field is pointing. But again, for both the sun sensors and the magnetometer, those measurements only really mean something to us if we know where we are. Right? And so it's kind of one of these strange chicken and egg things, right? That we'll tell you where you're pointing as long as you know where you are at first. Because depending on where you are in your orbit, the sun or the magnetic field will look very, very different. And so I like to think that's very similar to if I was to give you a sundial and you were somewhere in the world but you had no idea where you were and I asked you what time it was, you tell me, well, I have no idea what time it is, right? Because the only way that a sundial works is if you program it, right? Point it in the right direction, based on where you are on the planet, right? So clearly we need something a little bit more. And what that thing is that we need is our orbital position. So a lot of people say, well, what about GPS? GPS works great. And it does work really well in space. I did some of my master's research on that. But of course, you have to be below the GPS constellation in order for that to work. Which is usually the case. The GPS satellites are reasonably high, but it's still, it's a bit of a limitation. Many people have used in the past ground-based observations of spacecraft to calculate the orbits. In fact, we still use that quite a bit today, and I'll talk a little bit more about that. And we rely on our good friend Newton there to be able to predict where the satellite will go once we get some ground-based measurements from them. But my favorite, and probably your favorite also, is a star tracker. And so star trackers are the things that we use most often to figure out where we are pointing in space. And so typically the way that they work is it's some small telescope that takes a picture of the night sky. When we have that picture, we compare the small few stars that we see against the Hubble Guide Star Catalog. And we quite literally, what happens, well, I suppose it's not literal, but it's digitally, we slide our little picture across every possible area within the entire 4 pi steradian sky and look for the area of the sky that has the best match. And then we kind of tilt and rotate and twist the picture until we get something that matches quite well, and we say, aha, we know where the satellite is pointing. But there's a really interesting part of star trackers that I think make them even better than a sun sensor or a magnetometer, and that is that you don't need to know where you are in order for a star tracker to work. And you say, wow, why is that? And well, so the reason basically is just that stars are really far away. Right? And so my wife's a physicist, and so she jokes that engineers never calculate anything exactly, because we just calculate a number and then multiply by 3. Right? It's a factor of safety. Right? So for me, a star might as well be infinity away. Right? And so from a spacecraft perspective, that's pretty much the case, right? Because no matter where I am in my orbit, that star is pretty much always there. Whether I'm on one side of the planet or the other side of the planet, that small baseline means basically nothing to the angular measurement that we get from a star tracker. And I say it's very similar to what used to happen to these conversations I have with my mother and father when I'm in a car driving to, go camping or something in the summer. I'd say, hey Mom, that tower, that radio tower over there is moving with us. And she said, no, it's not, Philip, it's really far away. I said, no, it's not, Mom, I've been watching it, it's been in my window for the last 3 minutes. I can still see it, it's still right there. All the trees are whizzing by, but not that thing is moving with us, right? And so I remember starting as a kid, starting to realize, this perspective thing is kind of interesting, right? I can move around a whole lot, and the close objects seem to be moving, but the far ones don't. And so that's part of the reason why, well, that is the entire reason why star trackers are so useful, because those stars aren't moving, and they're so far away that it turns out to be a great guiding source. But I would like to do more with less. So what if we could find a way to use a star tracker for more than just attitude measurements or angular measurements? What if we could use a star tracker to tell us what our position is as well? And so in a way, that would be using what we usually use a star tracker for our attitude or our orientation, and a GPS receiver for our position. If we combine those together, well, first of all, could we do that in the first place? And secondly, do we even want to, right? And so when I bring this up with other engineers, it's funny. I have one camp of engineers that says, well, but why would we ever want to do that? If you've got a star tracker that works really well, that gives you your orientation, and you have a GPS receiver that gives you your position, and they both work well, why not just have both of those things and then just say you're done? What's the point of putting them together into one thing? And to some extent, they're kind of right? I mean, I have lots of these magical devices in my kitchen that claim to do everything, from it slices, it dices, it trains your dog how to go fetch, right? But do I really need this giant device? Is it better for me to have one complicated device than to have two somewhat simple devices? And the answer there may not be what you expect, actually. And so when I took this job at the U of M, it's an industrial research chair. I work very closely with Magellan Aerospace. They're always trying to find out new ways for us to kind of kick the space industry in the pants and say, stop doing everything the same way you've always been doing it before, because we're not going anywhere in space. We need to do it better. We need to do this much better and smarter. And so one of the ways that we think we might be able to reduce costs of the space program is if we could just have less parts. I mean, that sounds really simple. But the reason why is because when we build a spacecraft, this is like an exploded view of some sort of random spacecraft. It happens to be the Artemis spacecraft from the University of Texas. But it's an exploded view, and you can see, spacecraft are made up of tanks and thrusters and brackets and solar panels and batteries and computers and heaters, all of these things together. But every single part that we put on the spacecraft has a tremendous overhead associated with it, right? We have specifications and qualifications and handling and interfaces and software sometimes. We've got vendor management. We have to travel. We have to go see the vendor, make sure the vendor's nice. We have to go have dinner with the vendor, you know, and come back. We have to procure the thing. We have to inspect the thing. We store it. We install it. We align it. We have to have procedures for all those things. We have to test it. We have to manage its life. Eventually it's going to die. I need to have a plan for how I'm going to replace it. I need to watch over obsolescence and then risk, right? And so all of these things, no matter what the part is that I'm installing on that spacecraft, I'm doing most of those things with that part. It doesn't matter whether it's a bracket, a battery, a computer, or a reaction wheel. It doesn't matter how complicated that part is. I'm doing some subset of all of those things, and that's a cost. That's a cost associated with it. So it costs time. It costs money. And so even if we can have one slightly more complicated device, that's a pretty good plan. So going back to the star tracker, we started thinking, well, how could a star tracker tell us something about position? And is it possible that it could? So let's think about this again from like the measurement perspective. I'm measuring this position of a star that's like an infinity away, and when I move back and forth around my orbit, that star position doesn't really move. So that measurement probably doesn't contain any information about position. But what if we could get other measurements from a star tracker? So we started thinking in my lab, well, what if you're lost in the woods? If you're lost in the woods, how do you navigate? Okay, so maybe you have a compass and you can use that, and that would be nice. Maybe you have a GPS receiver, and that would be nice. But if you had none of those things, what do we typically do? Right? I mean, I spend a lot of time in the forest. I do a lot of hunting and hiking and camping. And so I mean, you know, one of the things that came to my mind was a Scooby-Doo episode that I watched once, where Scooby and Shaggy were running through the forest, and they saw some moss on a tree. And they said, moss only grows on the south side of the tree, right? So that it gets the most sun, right? But little did Scooby and Shaggy know that actually the bad guy had moved the moss from the south side to the north side just to confuse Scooby and Shaggy, right? But, you know, they were smart, you know, they figured it out. But, you know, anyway, that's a bit of an aside. There's no real moss in space anyway. But I got to thinking, well, what about logging roads, right? Like if I'm wandering through the woods, I stumble upon a logging road, I think, oh, well, I probably could follow this road somewhere. Maybe this road takes me somewhere interesting. Or maybe, what's even better, is that if I see a logging road, and I kind of have some idea of my map around me, and I know that there's an old logging road somewhere, and I stumble upon it, then I'm probably in that location. Or what's even better is maybe if I'm walking through the woods and I hear a truck go down the logging road, I think, that truck must be going to the logging depot or something, right? So I thought, well, could we do something similar in space? So there's no real roads in space, but there is stuff in space. There's a lot of stuff in orbit, right? And that stuff tends to be gathered in certain areas, like the geostationary ring we can see here. This is a simulation from many, many years ago. It's much more dense now, but many years ago, simulating what all the space junk looks like in orbit around this planet. There's a lot of it, right? So, and not only that, but there's so much of it. There's so much of it that people track it, right? So anything that's bigger than a few centimeters, anything that's bigger than about this big, is being tracked by NORAD using a mix of ground-based telescopes and space-based telescopes as part of our space situational awareness, right? And so this is kind of cool. So they're tracking all these objects in a similar way to how Hubble tracks, or tracked, the entire sky. So they're maintaining their own catalog, similar to the Hubble Guide Star catalog. And what's even cooler about this is that recently, because of all this space junk floating around, star tracker manufacturers have had to start writing special algorithms that reject images of space junk on their star tracker, just so that it doesn't confuse the star matching, right? So we thought, well, wait a minute. What if we use that information in the star tracker to help us with our guidance, right? And then instead of using the star catalog that we have from Hubble, we use NORAD's catalog of space junk, of predicting where those pieces of space junk might be. And what's even better about that plan is that, remember, the stars that we imaged were an infinity distance away. So when I moved from one side of the planet to the other side of the planet, that image didn't change at all, effectively, at all. Remember, I'm an engineer, right? Factor of safety, but pretty much not at all. But space junk, no, now all bets are off, right? These pieces of space junk, some of them are in low Earth orbit, some are in medium Earth orbit, some are in geostationary orbit. If I saw a piece of space junk somewhat accidentally with my star tracker and I didn't ignore it, that image does have position information embedded into it. So when I move each side of the planet, that's going to move a little bit, right? So we started asking our question, well, could this actually work, right? What kinds of things might go wrong if we tried this in real practice? And so these were some of the questions that we came up with, right? Well, what about numerical error, right? So I mean, we're effectively looking at something that might be like 10, 15, 20,000, maybe even 100,000 kilometers away. At what point does it effectively become infinity, right? And what dictates that? What about our knowledge of these objects, right? Yeah, NORAD is tracking them, but how closely, how accurately are they tracking them? What about observability, right? I mean, how well can we actually see these things? Obviously, they have to be in opposition. There has to be some light coming from it. Obviously, we're not looking at stars that are giant balls of fire, so we need the light to come from somewhere else and bounce off of it. So how reflective are these objects? How likely is it can we see them? How likely is it that we can identify them even if we did see it? Like if we saw something streaking by, we say, yes, that's part of a Soyuz rocket from July 2nd, 1972. Right? So I was trying to figure that out and do that kind of identification. That's a challenge too. How many of these things could we possibly see, and is it enough? Right? So we wanted to start this research program, and I'll tell you, I don't have every answer to all those questions, but we have some of them. We have some of them. So I thought we'd talk a little bit about this today. So let's talk problem geometry a little bit. So really what we're trying to do here, the idea is that we have some observer, some spacecraft that's in some circular orbit, let's say. And one of the things that's really important to me, and I'll get on my soapbox for a second here and talk about this, but it's important for me that when we start investigating problems like this, that I don't throw every effect I can possibly come up with in my simulation. We try simulations that are just complex enough to demonstrate an interesting effect, but no more complicated, right? Because to me, it's important that we narrow down on what the important and driving factors are of a certain concept, as opposed to just saying, well, we're going to do three-dimensional simulation and simulate the orbit as well as we can, and simulate the space environment, and simulate optics, and simulate this, that, and everything else. We started with something very, very simple, which is just a two-dimensional plane of motion, moving around in a circle, looking at some object, and that object might be a star, or some kind of a space object. We call them resident space objects, or RSOs in the distance, but we can just call them space junk. So the goal here then is, could we estimate our position and our pointing direction, our what we call our attitude? In this case, the attitude is the angle, the phi, or phi, from just measuring stars and objects. And then the question then becomes, what phenomena, like what parts of this problem become the limiting factor? How far can I see these things? How long can I see them? How accurately could that lead to an estimate? And so the first thing we need to do here is say, all right, well, let's think about our measurement. And so the measurement is really just some reasonably basic trigonometry, right? It's just the arctangent of the difference between our y's and x's, and we're subtracting off the attitude angle as well. And while that looks like a reasonably simple measurement equation, and it is, it turns out that the tangent function is actually quite nonlinear, and the arctangent is even more nonlinear. So more on that later, but needless to say that this measurement equation, while it looks relatively innocuous, the nonlinearities are kind of tricky. And so, yeah, so quite nonlinear, but we'll talk a little bit more about that a little bit later. So the first question we had to ask ourselves is, well, mathematically, does this even make sense, right? I mean, I think that physically it probably does, right? I know that if I'm sitting in a car, it looks like that tower is not moving at all, but the car that just passed us was absolutely moving. And so we started asking the question. So the first thing we did is we wanted to linearize that kind of wacky nonlinear measurement equation. And so this is kind of what we did. We said, well, could we represent this as some linear combination of some H matrix, let's say, times X? And so we did exactly that. We took some partial derivatives. We came up with what one row of our, what we call our measurement matrix might look like for some measurement. Now that measurement might be a star. It might be something really, really close to us. And so we wrote it in terms of this, just A. We called it some variable A. But we wrote A in such a way that you could see that if the distance from the observer to the thing that we're looking at is really, 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 really big, that distance would be Ri, that this thing just collapses to just 0 over 1, which is just 0. Which makes us feel kind of nice and warm and fuzzy, because now what I wanted to do is form a really, really simple Again, this is like a one-dimensional, only two-measurement version of it, just so we could wrap our heads around the mathematics a little bit. But if we wanted to come up with a scenario where I measure one star and one close object, let's say it's a Soyuz rocket or something that's still tumbling around in space, that's what my measurement matrix looks like. And we can actually highlight certain columns there. So that first column tells us the sensitivity of our measurement to position. And the second column tells us the sensitivity of our measurement to angles. And so not surprisingly, the star measurement only tells us something about angles. And the space junk measurement tells us something both about angles and our position. So theoretically, this should work. Now, mathematically, the way that it works is we take the pseudo-inverse of our measurement matrix, which is just the inverse of H transpose H. And then we can look at this matrix now and say, okay, a little bit of linear algebra tells us that this matrix should be invertible as long as A is not 0. So that made us feel nice, and this sort of reaffirmed what we thought must have been the case in our heads. But now the question comes, just because we can invert that matrix doesn't necessarily mean we should, right? So anyone who's ever worked with MATLAB or any kind of computational platform that's tried to invert a matrix and have MATLAB yell at you and say, matrix ill-posed, or bad condition number in matrix, I don't want to invert that thing for you, right? And we're obviously dealing with really poorly conditioned matrices because I'm trying to say that something that's like 10,000 or 100,000 kilometers away is actually reasonably close to me. So we're a little bit worried that we might not have enough numeric precision to actually do this problem. So we started asking some mathematicians. We said, well, tell me about precision. When I go to invert a matrix, what makes that hard? And so what makes it hard is the condition number. So the condition number C of the matrix and the machine epsilon. And so when we talk about epsilon is the smallest number that a computer can ever represent. The smallest number that a computer can represent. And so for most desktop computers, it's like 2 to the minus 17, I think. I forget the number. I should have looked it up first. But anyway, what this does is this tells us then how many digits of precision we get when we try to invert that matrix. And so to calculate the condition number, we need the singular values of that matrix, which is just the eigenvalues in this case because it's a special form. We can then form our condition number, and then that tells us, now what we have is our expected digits of precision as a function of how far away this object is. So, because what I'm really trying to do is figure out, because I mean, if this scheme tells me that this only works as long as I'm viewing objects that are 10 meters away from our spacecraft, then we've got much bigger problems than figuring out where we are. We've got space junk whizzing by us only 10 meters away from our spacecraft, right? That's kind of a hairy day. So we want to see, well, how far away could this actually work? And so we plotted it. And so it turns out, actually, then this is kind of interesting. So if we use a double precision computer, right, the kind of computers that we have on our desktop right now, we could technically, if we could see, and that's a big if, I'll talk about that in just a minute, but if we could see this space junk all the way out beyond the moon, we could technically still calculate our position to about an error of about 1 kilometer, which is kind of cool. Now, if we were using a single precision computer, which is kind of what we were using 15, 20 years ago in space, now we have double precision computers that are space rated, but in 10 to 15 years ago, it would be a much different problem. Yeah, we'd be talking hundreds of thousands of kilometers error. Because of the numerics of this, once we get out sort of beyond the geostationary ring. Now, you can see these all work reasonably well if we're in low Earth orbit, or maybe even medium Earth orbit, but the single precision still is totally up to lunch. So this tells us, we're like, okay, all right, so this maybe this works. We talked about the numerics of it. Well, what about how accurately we track these space objects in the first place, right? So NORAD is looking at these objects, they're watching them from the ground, they're watching them from space. How does this actually work? So many of you might be familiar with the two-line elements, the TLEs. These are the things that NORAD tracks, and they publish these every day to every few days for pretty much any object that they see. So this catalog of space junk is really represented by these two-line elements. So what we do is we take those two-line elements, we use some kind of an orbit propagator, like a simple generalized perturbation method, which I won't get into the details, but it's basically a relatively easy way to propagate orbits. And when we do that, we find that depending on how high this satellite is that we're trying to track, we could have errors of anywhere from 1 to 300 kilometers, which sounds large on sort of a terrestrial scale, but in an orbital scale, that's not too bad. That's not too bad. And in fact, you really only see those errors in the hundreds of kilometers when we're talking about satellites that are below about 300 to 400 kilometers altitude. And the reason why those are so hard to track is because of the drag. There's quite a bit of atmospheric drag. Now, I'm not talking the same kind of drag as what we see on an airliner. This is space drag, right? But it's a little bit of rarefied air that acts on the spacecraft that causes this drag to change the orbit quite rapidly. So the bad news is that we can't really track those spacecraft all that well. But the good news is they don't last too long anyway, right? Because they're going to be the first to re-enter. And so really, I kind of want to navigate from the ones that are in the 700, 800, maybe 1,000-kilometer orbits anyway. Those are the ones that have staying power, and luckily those are the ones that we can track with better than, say, about a kilometer accuracy. And oh, by the way, just because we like looking at pictures of satellites, one of Canada's space assets that we use these days to track objects in space is a spacecraft known as Sapphire. And so Sapphire is in space, and every day taking pictures of space satellites and space junk, and it has a really bad day when 2 satellites collide, because now what used to just be 2 pieces of space junk is now hundreds of thousands, maybe even millions of pieces of space junk. And so this is the job of DRDC, Defense Research Canada, and they use, one of the jobs of them, I guess, and they use Sapphire spacecraft. So, okay, so the next question then is, well, could we actually see space junk? Can we see that on a star tracker? Now, the answer we know is almost certainly yes, because star tracker companies have had to come up with ingenious ways to reject this. And in fact, the NEOSat spacecraft that this animated GIF is from is showing a piece of space junk streaking across the imager in one of its space junk sort of tracking modes, right? It's just taking the same picture several times over and over again, and it sees this piece of junk streaking across the sky. And so I thought at this point I was going to get into some specifics about looking at space junk, but I thought we all like talking about space telescopes, so I thought I would take just a minute and talk a little bit about NEOSat, because it was one of the spacecraft that I worked on. I did the guidance, navigation, and control for NEOSat, which is now in space and operating. And so I thought you might be a little bit interested, as a bit of an aside, while we're talking about this anyway, we can talk about NEOSat. So NEOSat is a Canadian Space Agency project that was originally conceived to put a telescope very similar to the MOST microsatellite, and many of you have probably seen data from, many of you might even know Jamie Matthews, an astronomer from the University of British Columbia, that was the principal investigator of the MOST microsatellite. NEOSat was basically MOST again, but with a giant apple. So it was the same telescope that we put in NEOSat was the one that was in MOST, and it was is a 15-centimeter, I'm going to say this wrong, you can all correct me, Maksutov? Did I say that right? Maksutov telescope. And if you're interested in the fancy engineering diagram, it looks like this. The detector on the right, on the left, and the mirrors on the right. So the idea with NEOSat was we had 2 missions, and this I'll tell you a little bit of politics about this mission, which got sort of humorous over time. We had one PI. We actually had 2 PIs. We had 2 PIs for NEOSat, 2 principal investigators. One of them wanted to find asteroids. One of them was very worried that we're all going to get smacked by an asteroid someday, and wanted NEOSat to detect asteroids so that we could predict when we're going to get the big smack, right? And the other one wanted to use NEOSat to track space junk so that other assets don't get smacked. We worry less about Earth getting smacked by space junk. We worry about Earth getting smacked by sort of asteroids. And so what's interesting about that is that these 2 principal investigators have very, very different worldviews about what this telescope needed to do. They both needed to detect things, but they wanted to detect them in very, very different ways. The asteroid part of the mission, they just wanted to see it. And some of those asteroids are very, very, very faint because they don't quite have the right opposition with the sun to get just enough light into the telescope. And and then the space surveillance crowd, they didn't just want to see the satellite, they wanted to measure precisely where it was because they were trying to estimate the orbits of those satellites. And let me just illustrate that dichotomy a little bit for you, because it might sound very similar. But so if I have a CCD, so let's say that this is like a 4x4, 4 pixels by 4 pixels portion of my detector, the detector on the telescope, and I have some dot of light from a star or a piece of space junk or an asteroid or whatever it is. And let's say that it lands right there, and it's very, very, very well focused, which is exactly what the asteroid people want, because they're trying to detect incredibly faint dots of light, and so they want that to be as focused as possible so that they can certainly light up those pixels. And if that's the case, we light up 1 pixel. And then if now we come along and the people that are trying to measure where the space junk is, they say, tell me exactly where that space junk is, their best guess has to be just somewhere in the middle of that pixel, right? Because you've only lit up 1 pixel, right? Now, on the flip side, if we purposefully spread out that light, using either Fabry lenses or we purposely defocus that light, now this star kind of shows up as a blob, right? And we spread out the light, but it lights up about 4 pixels now, right? And it lights them up with different intensities. And so when I now go to calculate the position of that dot on my array, I'm now doing a sub-pixel weighted average. So now I'm not quantized by pixels anymore. I now can do this sub-pixel interpolation. And so what's interesting is that the people that were trying to do space surveillance were on the right-hand side, and the people that were trying to detect asteroids were on the left-hand side. So we had all these arguments in the design meetings for NEOSAT about how tightly we should be focusing starlight. And what's even better about NEOSAT, actually, is, well, and MOST as well, is that unlike most spacecraft that have a separate star tracker and an instrument that you're always trying to sort of align the two of them, is that we used the science instrument as our star tracker as well. So at the back of our telescope, we had 2 CCDs. One of them was for star tracking, the other one was for science, which is perfect because it meant that I get this killer awesome star tracker to use because it's a 15-centimeter diameter telescope. Not too many people get to play with a telescope like that as a star tracker, which is kind of cool. But anyway, eventually we were able to convince the asteroid hunters that they should be blurring the light just a little bit. And so we came up with what we thought would be our optimal point spread function, right? The optimal amount of defocusing. Because of course there's a downside to defocusing as well. It means that I've effectively lowered my limiting magnitude, right? If I could have seen magnitude 14, maybe I can only see magnitude 11 now, or something, with my star tracker. So what we did is we did this over and over and over again. We ran this little optimization routine where we would choose a point spread function, and then we would walk through the entire Hubble Guide Star catalog and say, now, what areas of the night sky, or just the sky in general, doesn't have to be night, we're in space, right? So of the whole 4 pi steradian sky, how much of that sky can we actually look at? Which, as you can imagine, took a very long period of time, because the field of view of our telescope was only, I think, 0.8 degrees. And so we looked at every single 0.8 degree by 0.8 degree patch of the sky. And we walked through the entire sky. Of course, not just 2 beside each other, we had to look at overlapping ones too. And we said, in this patch of sky, how many stars are here that are brighter than our threshold that we set by the point spread function we chose? And where, not just how many stars are there, but where are they, right? So, and then we assigned an optimization cost to it, and then we went back over and over and over again. We iterated until we came up with the optimal point spread function. And so what you can see is on the left, this was one of the best parts of the sky to look at. I believe this was somewhere in the galactic plane because there's lots of stars to look at there. And you can see that we had plenty of stars to choose from. We always like to use a maximum of 5 stars. You could use more stars to come up with a guided solution. We picked the 5 that we circled there, and then we didn't use the ones in the middle. And the color corresponds to the visible magnitude of the star. But then on the right, this was the worst part of the sky that we had looked at. This obviously we would have a really hard time navigating. We only have 2 stars in the right smack on top of each other. So to get a good solution, we want them to be really far away. So that was kind of interesting. Now, but of course, you probably all know this too. When we defocus light, we don't get a really nice Gaussian point spread function. We actually get these things more like airy disks. But it all turned out okay anyway. It was able to defocus. And also I'm told that the CCDs bleed a little bit too, and that gets us some of our spread. And so NEOSAT now is actually doing quite well in space. There's had a few little failures here and there that they've been able to recover from. But I just want to show you a few pictures of NEOSAT tracking objects in space. So this is some recent photos that DRDC and CSA took of Neosat in tracking mode. And so the way tracking mode works is that we line up Neosat and then we initiate a slew. Like we have it just sort of dragging its image across the sky so that we're moving the spacecraft telescope with two moving dots. And so that's why the dots appear as dots, which correspond to Anik F2, the Anik F2 satellite, and this Wild Blue 1 satellite, which I'd never heard of before. But then all the stars in the background are streaking, right? And so this is how we image those things, and then based on the length of those streaks, and if our dots ended up not being streaks, or sorry, ended up not being dots but small streaks, it would tell us where those satellites are moving and what their orbit would be. Now, even though Neosat is not really a telescope for astronomy, that doesn't prevent us from using it as such, so we took some pictures of nebula. So this is a picture of the Orion Nebula as viewed by Neosat. But what I think is the coolest part, and it's a little bit selfish for me. I mentioned at the beginning that some of the satellite programs that I've worked on before, I worked on the RASC Constellation mission, which just launched earlier last year in 2019. And then, of course, I worked on Neosat as well. And so Neosat has the capability of imaging other objects in space. And so shortly after the RADARSat satellites were launched, they were all launched on one Falcon 9 rocket, Neosat turned around and took a picture of all three of them. So this was one satellite that I worked on, taking pictures of three that I worked on, all from space, which I thought was kind of cool. So this was shortly after the RCM satellites were launched. Right now they're operational, so they're spread out quite nicely in their orbit. They're evenly spread through the entire orbit. But right after they were launched, they were all kind of in a little train there, moving together. And this is a picture that Neosat took of those satellites. So all of this is to say that it is possible. It's absolutely possible for star trackers to see junk in space, see stuff in space. But could we always do that? So we went back and said, all right, so what dictates how well we can see something? And of course, it's the optical cross-section, this gamma sub V kind of thing. And so we looked at a lot of literature of people that have viewed satellites on the ground and from space and came up with some rough rules for how much magnitude of light we would expect to see from certain size satellites. And then we plotted this. And so this is kind of the money shot here. This is now saying, all right, depending on what size satellite you have, and how well you can detect things with your star tracker, this is about how far out they can get. And so we looked at two different kinds of star trackers. There's what we refer to as like a CubeSat star tracker. This is like an inexpensive sort of a toy star tracker. I call it toy. It's still running a few $1,000s. And then we compared it to sort of the Cadillac of all star trackers, which is Neosat, because Neosat is using this big 15-centimeter diameter telescope. And so what you can see here is that if you're looking at large satellites, like if you're looking at big pieces of space junk, and you're using something akin to like a Neosat type star tracker, we could probably see them out to about 30 or 40, close to 10,000, let's say. Let's say about 10,000 kilometers out. And then the smaller satellites, like a small CubeSat or something, we're probably limited to about 1,000 to 3,000 kilometers. Now, if we were using the kind of the lower end star trackers, we're probably limited to more 800 to 1,000 kilometers. But still, that's not too bad. So we came up with all this, and we said, great, let's see if we can actually do it. So we simulated it. We made the extended Kalman filter, and some of you may be familiar with how that works, but it basically takes measurements. We do some kind of a weighted average. We then combine that with some kind of a prediction step based on the dynamics that we think we know. We loop that back, and then what comes out the other end is our orbit estimate and our attitude estimate. And so we tried it, and this is our fancy wiggly line plot that shows that, yeah, you know, it seems to be working for a little two-dimensional example with errors that are approximately on the order of like 10 to 30 meters error, let's say. But we cheated. We cheated a little bit. Just now, we told people we cheated, so it's okay. But one of the things, when you make these, and this, by the way, the reason why we used an extended Kalman filter is because we had to linearize what was turned out, and I had mentioned before, I was going to talk about this later, a very nonlinear measurement equation. And because of that, it's sort of all bets are off when it comes to a filter trying to predict how confident you should be in this answer. Right? And so the dashed lines are the filter's estimate of how erroneous the answer probably is. And you probably look at that and say, oh, that's not bad. That's not bad. It's kind of bounding and okay. But to get that, yeah, we kind of fudged it a little bit, right? And so the way that filter designers fudge it is they jack up the what we call the process noise in order to make it kind of work. And you can do that in simulation because I know how erroneous it is, and I can bump it up until it looks about right. So we kind of cheat, right? So if you're using this in space, yeah, it's not that good. It's not that good because how do we know that this estimate is any good at all, right? Because imagine if I told you, I said, okay, so I'm going to give you this like fancy navigation routine, and you're going to use it in space, and sometimes it might not work. You good? You're like, yeah, no, I kind of want something that's really going to work. And if it doesn't work, at least tell me it's not working. Right? I'm like, yeah, I don't know. These nonlinear filters, they're not so good at telling you when they're not working. And that's not very good at all. Right? Because what we need in order to adopt new technology in the space industry is confidence in this stuff. Right? We need to be confident in it. We can't just have these crazy academics walking around and say, oh, no, I think it's going to work most of the time. So just trust me. Just use it in space. It'll be okay on your billion-dollar spacecraft. Right? This is why we're so stagnated in the space industry right now as it is. Right? And so it reminds me actually of the time whenever I go driving somewhere with my wife. By the way, this is what I look like under the beard. This is like a long time ago before the beard, right? So my wife used to see a picture and she said, "Phil, do you know where you're going?" And I'd say, "Yes, absolutely, I know where I'm going." She goes, "You have no idea where you're going to." She says, "When you are not confident in something, you replace confidence." You replace knowledge with confidence. That's what she says I do. And I say, well, you know what, that's true. That's true. I do exactly that, right? But confidence is important, right? So how do we get confidence in these crazy nonlinear estimators? And so one of the areas where I think we do a really good job with confidence is something like GPS, right? So GPS, which we all use all the time, and you may not know that this is happening under the hood, but of course GPS has a whole bunch of satellites in the sky, and but one of the things that they do, and they do this very, very, very well, is they do this thing called geometric dilution of precision. And basically what this is the GPS receiver knows where all the satellites are that it's using to triangulate the position from. And if those are in a really good position, like really well spread out, I'm getting lots of angular deviations, then it says, my estimate must be really, really good. And you have a very low geometric dilution of precision. But if all the satellites that you're looking at happen to just by chance be all clumped together in one blob, that's going to give you a really bad estimate. And so the GPS receiver has a reasonably good guess at how accurate your position is. And we all use our iPhones all the time, right? My wife uses it to track me, and yeah, sure, I use it to track her too if I know how long it's going to be before she gets home. And sometimes you see the big blob around the little happy face of the person, and sometimes you see the little blob, right? And that's all based on the GPS's estimate of how good that estimate is. Right? You're estimating the confidence in your estimate. And that makes us feel really good, right? It makes us feel really good because we know that we're using an estimate that we have some idea that it's fairly decent. But one of the things that, again, this is a minor aside, but because I'm trying to innovate and try to kick the space industry in the pants, we're trying to find new ways to use technology. We need to make sure that we are confident in it so that we don't fall into these terrible design cycles. And I'm going to say a colleague of mine, Rob Z, who runs a spaceflight laboratory at the University of Toronto, and he talks about these two different cycles where he says, if we have a fear of mission failure, this leads us to want to test more and more and more, right? And we take more time, and the more we test, the more these missions cost a whole lot of money, and the more they cost a whole lot of money, then we don't have enough money in Canada to make more of them, right? So we decrease the quantity of missions, and the more we decrease the quantity of missions, the more we think, hey, well, better get it right. Right? Because we only get to build a satellite once every 10 years in Canada, so let's work really, really hard to make sure that it absolutely works. And the harder you work to make sure that it works, the more money they cost, and you just spiral yourself into the ground in this vicious cycle, right? But on the other hand, if we can start to accept mission failure or start to have more confidence in the technologies that we're putting in space, right, then we still test, but we test smarter. We verify, we're not as worried, right? And so the more we verify, our mission costs now start to decrease because we feel a little bit about this, we're testing things smarter. The more our mission costs go down, the more opportunity we have to make more of them. And the more of them we do, the more we can accept as mission failure. And this we call the virtuous cycle, right? But to be in this virtuous cycle, we need to have technology that we trust. We need to have technology that we trust and not something that's boneheaded academic like me has just gone away and written a journal article about it and said, don't worry, I've solved the problem and it works 80% of the time, then yeah, those 20% of the time you're going to be in a really bad place, but don't worry about that. I'm sure your building another spacecraft will be nice. Right? So we need ways to fix that. And so this is kind of where we are. I said we haven't quite solved the whole problem yet, although I will say that the next paper that we're writing right now, where actually my PhD students are working on another paper using a different kind of filter called the unscented Kalman filter, which is as weird as it sounds, right? I don't know who comes up with these names, but I don't even really know why they call it unscented. And the other one didn't smell that either. But it basically what it does is the extended Kalman filter had some linearization stuff. The unscented Kalman filter doesn't linearize anything. And so what we have found, and we're cautiously optimistic, we're preparing a manuscript right now, but cautiously optimistic that when we do this, we don't have to fudge anything. Our covariance estimate is better, much, much better. It's accurate more like 98% of the time, and that other 2% of the time, it's not so bad that it's going to make anything go crazy. So we're pretty happy about the unscented Kalman filter. We're looking at using some other kind of boundedness magic spells, known as Lyapunov style boundedness for estimator confidence, so that's kind of nice. We're going to test some of these. We're building a cube satellite right now in my lab, and we hope to build another one very soon. And we'll test out some of these algorithms in space. And then I also wanted to leave us here too with this concept known as SOUP. So SOUP stands for Software of Unknown Pedigree. And that might sound kind of like a strange way to say SOUP. But when I used to work in the drone industry, I sort of left that out. I worked in the space industry for a while, and then I built drones for a while. And part of the effort of working in the drone industry is trying to convince the regulatory bodies like the FAA that we should be flying drones in the national airspace, and they don't like that too much, because that's where people fly. But the problem with the drone industry is that it's all a whole bunch of kids that just graduated from university and they have a startup, right? And so none of them know how to write software to the standards that the FAA wants them to write software. This crazy DO 178 stuff, which is crazy software lingo for basically write software till you're dead, right? It's test it and test it and test it, and nobody wants to do that because all the kids coming out of university are writing open source software, right? And so eventually we convinced the FAA, I say we, I was on the committee that worked on this, but it wasn't me, it was sort of we, convinced the FAA that what if we could adopt this technology known as SOUP, which basically says we're going to try new stuff, but we're going to put a really strong firewall around it, so that if my crazy whiz-bang algorithms go crazy, don't worry, they're going to be caught by this wrapper, and we're not going to let the crazy software get out, and it's not going to endanger the national airspace where everybody else is flying. And so we're trying to say, well, maybe we do something similar in space also, something that will allow us to continue innovating. But I think really, if I could leave you with just sort of one last comment, and I'll tie it right back to CSI, right? I say, I like being an investigator and pulling information where maybe it wasn't there before. Is that I think that CSI just needs to have more rocket science. They were I can be part of their show. So anyway, I also wanted to thank the people that fund this really cool research from NSERC and Magellan Aerospace and the Canadian Space Agency. And I just wanted to thank you again. I always enjoy coming and speaking with you all. It was a really good time. So thanks for your time tonight, and I'm happy to take it. I appreciate it. Thank you.
Okay, that'll conclude our meeting for January the 10th. We'll continue on at Boston Pizza, where we're going to talk about drinks. I think I'm going to do that. Before we go, I think Stan wants me to mention about viewing the thin moon from the car.
Yeah, you don't necessarily need to be outside. If you're going to try the one in January, you could probably do it if you, first time around, from the warmth of the inside of a car, just roll down the window and with a pair of binoculars.
Okay, we can try that, okay.
Let me get more people testing it. Let me know how you succeed.
Okay, we'll see you guys at Boston Pizza. Come to the highway. Thanks.